Welcome to our continuing discussion of solutions of the diffusion equation in the limit of low Peclet number where convective effects are neglected. We were discussing the heat conduction in a composite material which consisted of a matrix in which there were embedded particles, spherical particles of size of radius r. In which the matrix had conductivity Km, thermal conductivity. The particle thermal conductivity was Kp, and the difference in temperature across the length of the composite material in the direction of temperature variation is L, and there is a temperature difference delta T applied across it. And we wanted to find out what is the thermal conductivity, effective thermal conductivity of this combination of matrix and particles. That is, if Z is the direction of variation in temperature, then the heat flux as a function of the temperature difference divided by the total length delta T by L. This coefficient K effective, we wanted to find out how this depends on the matrix conductivity, the particle conductivity, and the properties, the radius of the particles, number of particles, and so on. In the dilute limit, where the temperature disturbance due to the presence of one particle does not affect the temperature field around another particle. So, the particles are well separated by a distance comparable to, or by a distance that is much larger than the particle diameter. So, that the disturbance around one particle which will propagate to a distance approximately comparable to the particle diameter does not affect the temperature around another particle. In that case, each particle can be considered to be in a temperature field which has a linear variation in the z direction far from the particle. So, T is equal to T prime z far from the particle, where in this case z is defined as the vertical distance from the particle center. So, you have a linear temperature variation far from the particle. Of course, as you come closer to the particle, because the conductivities of the particle and the matrix are different, there is going to be a disturbance to the temperature field due to that, and we had calculated that. Now, we have to calculate what is the average flux. Note that in this case, this T prime is equal to the applied temperature gradient delta T by L is T prime in this case, because the temperature gradient far away from the particle where there is no disturbance to the particle has to be equal to the macroscopic temperature gradient delta T by L. The heat flux of course changes depending upon whether we are in the particle or in the matrix, because the conductivities are different. The total heat flux, the total heat transfer rate is going to be a combination of the transfer rate through the particle and through the matrix. And you can define an average heat flux. You can define an average heat flux, Q average in this case is equal to 1 by V integral over dV times the local heat flux, where this integral is carried out over both the particles and the matrix. So, this is the average flux, the volume average, which will give you the total rate of transport of energy per unit area perpendicular to the direction of the heat flux. And this consists of two components. One is the heat flux through the matrix, and the other is the heat flux through the particles. So, I can write this as integral over the matrix of dV In the matrix, the heat flux in the z direction is equal to minus K matrix into the gradient of temperature So, the heat flux is equal to minus of the K matrix times the partial derivative of the matrix temperature with respect to z plus the integral over the particles of dV minus K particles into partial T of particles by partial z. I will just use the temperature field as T here, whether it is in the particles or the matrix. So, over the particles it is the particle temperature, over the matrix it is the matrix temperature. Now, the second term here I can rewrite slightly. The second term here I can rewrite slightly. I will write it as the sum of two parts. I am sorry, there should be a 1 over V outside everywhere. So, this integral over the particles of minus K p times the temperature gradient, I have written it as sum of two parts, minus K m times the temperature gradient minus K p minus K m times the temperature gradient. You can see the factor of K m times the temperature gradient will cancel out in both cases, and it will reduce to what I had in the line above. Now, this summation over the particles plus the matrix is a summation over the entire composite. Particles plus matrix is a summation over the entire matrix, and I will get 1 over V into integral over the composite dV times minus K m into partial T by partial z. This is now as an integral over the entire composite, and then I have the second term, which is plus integral dV minus of K p minus K m. So, you can see that this separates out the flux into two parts, one of which is the integral over the composite of the matrix conductivity times the temperature gradient. The second is the integral over the particles alone. This is an integral over the particles alone of the difference in thermal conductivity between the matrix and the particles times the temperature gradient. So, this second term is the excess flux resulting from the fact that the particle conductivity is different from the matrix conductivity. So, it is the excess flux. The first term is just the flux over the entire medium if it were just composed of the matrix alone. In the first term, I can take out this K m because that is a constant. So, I will just get minus K m integral dV over the composite. This 1 over V times integral over the volume of dt by dz is the volume average of the temperature gradient. Okay, it's the volume average of the temperature gradient over the entire composite. Okay, so, this is just equal to the applied temperature gradient. Okay, this is just the volume average of the temperature gradient over the entire composite has to be just equal to the applied temperature gradient, which is equal to T prime, okay, minus Km T prime, okay, where T prime was equal to the applied temperature gradient. Okay. T prime was equal to the applied temperature gradient. Okay. So, this is the average heat flux you would have had if there were only matrix. Okay. And then the second term is an integral over the particles dV, okay, and I have a 1 over V here. Okay. Note that 1 over V times integral over the volume is the average temperature gradient, and on the second term I have 1 over V multiplying it, and I have minus of Kp minus Km. Okay. So, this second term is an integral over all the particles. Okay. This second term is an integral over all the particles. The particles are non-interacting, dilute limit. The temperature field around one particle does not affect the temperature at another particle. Therefore, this summation over all the particles is going to be equal to the number of particles times this integral over one particle. Okay. So, this is going to be equal to minus Km T prime minus Kp minus Km into the number of particles divided by the total volume, integral over one particle dV times partial T by partial Z. Where n is the number of particles, okay, and V is the total volume. And this is what we had solved for earlier, if you recall, by solving the equation, okay, for the temperature field around a particle using spherical harmonic expansions. A particle placed in a temperature field that is linear as r goes to infinity. We had used an expansion in Legendre polynomials and identified the coefficients in this polynomial expansion. All coefficients were 0 except for the coefficient corresponding to n is equal to 1, because as r goes to infinity there was forcing only for the coefficient corresponding to n is equal to 1. So, all coefficients were 0 except for the coefficient corresponding to n is equal to 1. And we had derived what is the temperature in the matrix and the temperature in the particle. Okay. So, the temperature in the particle was equal to 3 T prime into r cos theta by 2 plus K r, or 3 T prime Z by 2 plus K r. In the matrix it was T prime r plus this correction due to the presence of the particle, okay, 1 minus K r r cube T prime by 2 plus K r into r square. This we had calculated in the previous lecture, okay, using spherical harmonics expansion, identifying that there are non-zero coefficients only for n is equal to 1 in the Legendre polynomial expansion, solving and imposing boundary conditions, continuity of temperature, that is the temperature on the matrix and particle side are equal at the interface, and continuity of flux, the flux on the matrix and particle side are equal at the interface. Okay. So, this implies that partial T by partial Z is equal to 3 T prime by 2 plus K r, okay, where K r is the ratio of the thermal conductivities of the particle and the matrix. Okay. So, that was the solution that we got. Okay. So, I substitute that here. Okay. integrated over one particle. Okay. Integrated over one particle, and note that this temperature gradient is independent of position. Okay. dt by dz is independent of position. Okay. You can see that the temperature is proportional to z to the first power, and therefore dt by dz is independent of position. Okay. So, this is equal to minus Km T prime minus Kp minus Km, okay, n into the volume of one particle, okay, by V. Okay. Since times the volume of one particle divided by the total volume, okay, times 3 T prime plus by 2 plus Kr, because I am taking integral of a constant over the volume of one particle. Therefore, I get only the volume of the particle times this constant. Okay. And this number of particles times the volume of one particle divided by the total volume, okay, that is equal to the volume fraction. Okay. Okay, it's the volume fraction of the particles, or the fraction of the composite material that is occupied by the particles. Okay. So, this is equal to minus Km T prime minus of Kp minus Km into into 3 T prime into the volume fraction by 2 plus Kr. Okay. I can take a common factor of Km times T prime out. Okay. So, this is equal to minus Km T prime into 1 plus 3 into Kr minus 1. Okay. Times the volume fraction divided by 2 plus Kr, okay, where Kr is the ratio of the thermal conductivities of the particles and the matrix. Okay. So, this is the what we were looking for, the average flux minus Km, sorry, times T prime, where the effective thermal conductivity is equal to the matrix thermal conductivity into 1 plus 3 times the volume fraction times Kr minus 1 by 2 plus Kr. So, this is the final expression for the effective thermal conductivity of a matrix consisting of particles of thermal conductivity Kp in a matrix of thermal conductivity Km in the dilute limit when the volume fraction of the particles is small. The correction is proportional to the volume fraction of the particles. You can see that if Kr is equal to 1, that is if the two conductivities are the same, you just recover back the matrix thermal conductivity. If the particles have a higher conductivity than the matrix, then the effective thermal conductivity is higher than the matrix conductivity, and if the opposite is true, if the particles have a lower conductivity, then the effective conductivity is less than the matrix conductivity. Moreover, the effective conductivity depends only upon the volume fraction of the particles. It does not depend upon the diameter or the radius of the particles or their number. It depends only upon the volume fraction. Okay. So, whether you have large or small particles, provided it is dilute and provided the volume fraction is the same, you will get the same effective thermal conductivity. And the other thing to note is that this is applicable only in the dilute limit, where the volume fraction is small, the first correction due to the presence of particles in the matrix. As the volume fraction increases, the temperature field around one particle will be affected by the disturbance due to another particle, and you will have other terms in this correction increasing proportional to phi square, phi cubed, etc., where phi is the volume fraction. So, this is the only correction that in the dilute limit. Okay, this is only in the dilute limit where the volume fraction of particles is small. So, this is the final expression for thermal conductivity, and to summarize the procedure that we had used, we had a matrix, a composite made of a matrix and spherical particles of radius r, and the dilute limit, where the disturbance due to particles did not influence the temperature around another particle or the neighboring particle, because the distance is sufficiently large. In that case, for a particle with thermal conductivity Kp in a matrix with thermal conductivity Km, we had solved the equations del square of the particle temperature is equal to 0, del square of the matrix temperature is equal to 0. At the surface of the particles, we had Tp is equal to Tm at r is equal to r, and minus Kp, the heat flux in the perpendicular to the radius, is the same in the particle and the matrix. Okay. And finally, the condition that the temperature is equal to T prime z cos theta, sorry, T prime z okay, as r goes to infinity. Okay. So, these were the equations that we were solving. Okay. These were the equations that we were solving, and this T prime r cos theta could also be expressed as T prime r times P1 of cos theta. T prime r times P1 of cos theta was an alternate expression for this matrix temperature as r goes to infinity. Okay. As r goes to infinity. Okay. And based upon this, applying the boundary conditions, we could just infer that both the particle and the matrix temperature had to be in the form of a Legendre polynomial expansion, because that was the orthogonal functions using homogeneous boundary conditions in the theta direction for the equation del square phi is equal to 0. Okay. So, you got a expansion in Legendre polynomials, which are orthogonal polynomials. And therefore, you can express both the boundary conditions at the particle surface and the boundary conditions as r goes to infinity in terms of these Legendre polynomials. Okay. And if you do that expansion, you find that as r goes to infinity, the only non-zero term is due to P1 of cos theta. Okay. All other terms are 0. Okay. And the boundary conditions at the surface are homogeneous in the sense that they relate particle temperature to matrix temperature and particle temperature gradient to the matrix temperature gradient, and therefore, the solutions necessarily have to be of the form T particles is equal to a particle. Okay. okay, where these constants were determined from the boundary conditions at the surface. Okay. In particular, this term had to be 0 for the temperature to be finite at the center of the particle, and this term had to be T prime, okay, for the temperature to match with the linear gradient as r goes to infinity. And we had determined these two other constants A1p and B1m from the boundary conditions. From that we found out what is the temperature gradient through the particle. Okay. And that temperature gradient through the particle was what was related to the disturbance to the heat flux. Okay. This temperature gradient through the particle was the cause of an excess heat flux due to the presence of a particle. Okay. When the particle and matrix conductivities are different, you get an excess heat flux due to the presence of the particle that is proportional to the gradient of the temperature within the particle. And so, substituting what we calculated from the spherical harmonic expansion, we were able to find out what is the average flux and therefore, what is the temperature gradient. Okay. So, that was the procedure that we had used in this particular case. Now, this particular situation was a special case because it was axisymmetric, as there was no dependence on the meridional angle phi. Okay. In this particular case, it was an axisymmetric temperature profile. Okay. In general, one would like to solve the Laplace equation for a general non-axisymmetric case, where there is in general a dependence on the meridional coordinate. Okay. In this case, you have to use separation of variables, where you separate the temperature field, for example, into 3 components, one of which depends upon r, one on theta and one on phi. So, the equation of del square phi is equal to 0 for a general non-axisymmetric case is 1 over r square d by dr of r square partial t by partial r plus 1 over r square sin theta d by d theta sin theta partial t by partial theta plus 1 over r square sin square theta partial square t by partial phi square is equal to 0. Okay. So, this is the general non-axisymmetric case. We have solved this only these two. Okay. So, what happens if you have a variation in the phi direction? I will discuss this in the next lecture, the solution of the Laplace equation for the temperature field for a general non-axisymmetric temperature profile. This I will start in the next lecture. I will see you then.